Welcome back, everyone, to another hands-on approach to what we're going to be looking at for pattern blocks. So we've kind of done a lot of work now with the pattern blocks on fractions, and now we want to look at maybe all the other aspects that we could be using our pattern blocks for. So not in any particular order of importance. Maybe some logical starting points, but really you could be wherever and whatever grade you're teaching that you're going to be using different aspects of what we're going to talk about today. So I will pause the video in between the different topics if that helps a little bit, but not necessarily, like I said, in any one particular order of importance. So we are going to look at just sort of basic understanding of the pattern blocks to get going. And a logical place for us to start with students would be something like, you know, letting them learn the different shapes and the patterns. And for the younger ones, just having a pattern where they can start to take the blocks and that they can practice to match them up. And as they start to match them up, we can start to teach the names and all of those different pieces. So this is just one opportunity for them to start to become familiar with them. So this would be a very early on type of activity that we would have. There are all kinds of different patterns that you can download from the internet that you're able to access. I did put some into our opening video as well, but you can see some here. And then you also see sort of the start even of a conversation here, not for obviously starting grades, but here comes the symmetry, right? If this was our line of symmetry, here's what I want to see on one side. Can I build one side and can they show the other? So just sort of grabbing some of the different pieces that we have along the way. And they start from everything from quite long and complicated or easy, sort of like the caterpillar, or to something like even our little penguin that we have here, where they just start to get introduced to the different shapes that there are. So that would be a logical starting point. Okay, and there's a whole bunch of those. Like I said, I've got some listed for you on the website that we, our opening video, sorry, that we went through. And then I might do something like, what if I had these two different shades of triangles, right? I'm just leveraging the fact that they came from different manufacturers. So then we get into just the basic patterning. And can they identify what the pattern is, that it's a light green, a dark green, a light green, a dark green, that they're triangles, and then can they extend that pattern? And then we try and go beyond just having, let's say, one shape. We might go into having triangle, maybe two rhombus, another triangle, and then start with the next rhombus, and what would it be to finish that pattern, and can they extend it? So it's just working on different attributes. In this case, it's color. Remember that the word that we look for is the core. The core in this case is a light, dark, so it's light, dark is the core. Here it's triangle, rhombus, rhombus, or light green, blue, blue. Or it's a double one, right? Because I can express it in both of those. So it depends on where it is that you want for the students to go. And once they understand core, they understand patterning, they can extend it. Of course, we're going to ask them to create one of their own. So can they create a core that has two shapes in it, whatever they pick? Okay, there's my two shapes. We haven't used those a lot lately. Can they create another extension of the same thing? So we would be looking at, they would grab the same skinny rhombus and another square, and then so on. So that's kind of a logical piece. And that doesn't mean we have to stay with just the basics. Remember that we can also extend those to be inclusive of our deci blocks. So I might start with the purple, another purple, have a boat. Okay, and then I might even have a small triangle, right? So I'm using four different, my core has four different values in it. So dark purple triangle, the boat, and then the small triangle. And then again, can they reproduce that? So that's kind of a good starting point for us. We want students to become really familiar and comfortable with the names so that when we're calling out patterns, we can even say, instead of just showing them the pattern, can we call out the shape and have them lay that shape down? so that they're creating a pattern as we're calling it out to them. We might even ask them to do something like this little diagram. So once they become really familiar with it, we can say, can you create this one? So this is a smaller version. These are not drawn to scale, obviously, but can they reproduce this now? Can they see this and then can they create the same shape that they have? And once they get good at doing some of these different pieces, then we might even want to say, you make a pattern, you make an animal or an object that you want to make your shape out of, and have your partner reproduce it. Or they can even trace it on a piece of paper. So instead of me just having this picture, I might build the whole thing, or I build my own, and then I trace it on a piece of paper, and then I give that to my partner, and I say, can you make the same shape? Can you figure out what I used inside? And that just adds a little bit more challenge to it and makes it a little bit more fun for the students, for sure. We also want to give them opportunities to, this can get into tiling the plane, but on the same token, it's still just using what patterns fit together, which blocks can I fit together, which ones would have holes in between if I tried to do that. And then we can also even have a conversation with them if they're a little bit older about how does that dark color kind of make it stand out? Why does it almost looks like it's coming right off the page? It's actually standing up off of the page, so that they start to learn that dark and light colors together can give us a bit of a different perspective of depth. And again, it makes it look like this part is sticking right out. And in fact, it's not, it's just laying on the paper. So again, having them just doing some practice, coming up with some shapes that they can see that would maybe stand out a little bit more. This would be a great one for them to just reproduce. Other ones that would be great is taking Métis patterns. You can also have all different kinds of First Nations patterns that you could recreate with different colors, same colors, and have the students design them and come up with that. So there's a number of these, again, that are available. But it just also gives us some conversations, not just about the shape. Now we can get into the art part of it. We can get into depth and perspective, because those are all pieces that students need to recognize are just bits and pieces of these little blocks that we're calling pattern blocks. So here it almost looks like you have two chairs that you can sit in the corner, that this is actually gives you a perception that you could lean against the backs of these, where in fact these are just flat on the table. So good opportunities for students when they're getting just to learn the pattern blocks. As we get into older students, these tiling the plane conversations come into play. So we would want them to become proficient at just playing with the different kinds. Okay, we might have them when we're doing the patterns. Grab another one here that I recreated. When we're doing some patterns, and we're asking them to, I'm just going to get the focus going here. There we go. So I've got one that's already done, and I might show them that and say, can you recreate the first one? So can they come up with the picture of, it doesn't really matter if it's a dark green or a light green, but we want them to recreate it. And note that it actually has some pretty distinct angles to it. So this one at the top here almost looks like it's kind of straight. So I'm going to make sure that I turn mine so it reflects this. And now we're asking them, now that they see the pattern, what would the next block be over here? So can they recreate that? So this is an opportunity for them to realize too that not all of them have to be just single blocks as they go along. I can recreate a pattern that is got multiple blocks invested in it. Further to that conversation, we might want to have a conversation then about, what about this pattern? Where I see the pattern is starting to increase. So they talk about increasing patterns and decreasing patterns, and I could flip this around and make it decreasing. But here I have a square and 1, 2, 3, 4 of the skinny rhombus. And again, they could build that using our squares, right? They can do it this way. Then they also realize that everything is the same size, same length on it. So they could build exactly the same model. And then we could say, Well, what's the total number that you have here? So let's look over here. Well, I have the same original, and now I had 5 over here, 6, 7, 8, 9. And then when I do it one more time, I would have 10, 11, 12, 13. So I went from 5 to 9 to 13. What do they think the next pattern would look like? And how many do they think would be in there? So that would be an opportunity for us to even label this as figure 1, figure 2, figure 3, figure 4, and we could set up a table based on the figure, what was the total number of blocks, and then what is the increasing pattern. So we're now getting into some higher order thinking again, but we're looking for patterning, not only patterning in the design, but patterning in what's happening algebraically, that they're adding 4 unique shapes each time to the total. And can they predict what maybe the 7th one would look like? So they can look at the pattern that's here. Can they take a guess? Could they build it? And then double check. Did they come up with it correctly? How many do they think would be in the 7th one? So again, this is obviously not the beginning years. This is students who are dealing with patterns that are increasing and decreasing, but they're making predictions. They're using their knowledge of what they're seeing in the pattern growing and shrinking to make a prediction, and then they can double check their prediction as well. Let's look at another pattern and another way for students to start to see some things that could be happening. So I start with one small triangle. And in this case, each side length is 1, 1, and 1. Okay, and it doesn't matter what that unit specifically is. It's just 1 unit, and it's consistent 1 unit because this is an equilateral triangle. So here I start with 1 triangle, and I have a total distance of 3 around the outside. When I change the length of the side to be 2 on each side, what I've really done is I've added another triangle to the bottom here, and another one, and I had to fill one in between. So now in the second step, I have a total of 4 triangles. And the length of the side all the way around is 2 by 2 by 2. So if I wanted to say perimeter over here was 3, 1 plus 1 plus 1. Perimeter over here was 6, 2 plus 2 plus 2. Let's look at what happens when I try and put 3 of them on each side. So I have 3 here, 3 here, and 3 here. And then I had to fill in the center pieces. So how many triangles do I have? We've already counted this once before in our other one when we were talking about fractions. But in case you're watching this for the first time, I see 1, 2, 3, 4, 5, 6, 7, 8, 9. So the large triangle that we have in the deci blocks fits 9 small triangles. So in this case, I have a total of 9 triangles inside, and I have 3, 6, 9 is my perimeter. So I can start to see patterns that are happening too. And again, this will depend on the age of the student that you are working with. So we might say, what do you predict will be the next triangle? And what do you think the perimeter will be for that one? And they can start to see a pattern that's happening. And then over here, I also see a pattern that's happening. But you're going to have to be a student who's a little bit older to understand what that pattern is. So in this case, what I'm seeing is 1 squared. Here I'm seeing 2 squared. Here I'm seeing 3 squared. So I'm going to predict that my next one will be 16 or 4 triangles all the way around the outside. So again, I'm seeing that that's going to be quite a bit larger. But what I'm seeing is that I'm seeing the numbers that are becoming squared as they go through, based on the lengths of the sides. And if each one of these is 4 on each side, then I know that the perimeter here is going to be 12, but I can also see that it's increasing in groups of 3s. So again, this is not just about playing with the blocks. It also becomes very algebraic at this point. And so for students who are in junior high, it would be valuable for them to get the pattern blocks out to do this kind of work, set up the tables, and then they can start to make those deductions as they go through. Squares and cubes, those would come up in numbers that would be more in the junior high area. But nonetheless, we would have that opportunity to have that conversation with students. And even if they don't know 4 squared and 3 squared, they can still figure out that it's going to be 16 simply by putting them together and then coming up with the total value. So again, it gives us some opportunities to talk about this. We're going to move into area and perimeter right away now. All right, let's revisit our hexagon and our large triangle again. So here's what I've got as my basis, the original hexagon, and then I have the new triangle from the deci block. And in terms of the triangle, the small triangle, and that's important for us to say because it would change if we had a different measurement tool. So right now we're going to just use the small triangle, the small equilateral triangle, and we're going to say that this is 1 unit squared. Whatever that unit is insignificant at the moment. We're just calling it 1 unit squared. So then how many of those unit squares does it take to cover a hexagon? We already know that that's 6. Each one of them was 1/6. And when we had the large triangle, we just counted them. The total was 9. So the area that I need to cover, or how much I need to cover in terms of the small triangle, the large triangle, I would need 9 small triangle or 9 units squared. So students can then go through and figure out all the different areas of the different shapes, every shape that we have. And some of them they're going to already have memorized because they know that this one has 3, this one has 10, this one has 5, so they can figure those out. But if they don't, there's nothing stopping them from taking the triangles and putting them on to figure out what is the area that gets covered. And then as students start to get a little bit better and faster at remembering, they're also going to realize I don't have to always build 5 triangles on a 5. I might take fewer blocks just because it's easier for me to deal with. I already know that 6 go on there. I already know that 2 green triangles go on each of the blue trapezoids. So instead of building out 6 greens, 2 greens, and 2 greens, I'm just going to be really efficient here and try and just build it with fewer number. And I know that this is 6, 7, 8, 9, 10, which is correct. So they can start to build different shapes that have the same values, that they can create equivalent values. So the next task would be for them to figure out what are all the different areas, if we're assuming that the green triangle, the small green triangle, is our unit of area squared. Okay, that's our base unit. How do we express all of the other shapes in terms of that small green unit? And that's important, again, like I said, for us to say, because if the unit was a blue hexagon, then it would be a different unit that we're measuring. And we wouldn't necessarily have the same values because only 3 of them fit on here. It wouldn't be 1/6, it would be 1/3. And not every shape would be able to hold a blue rhombus on here. I'm only going to get 1.5 of one. So I would get different kinds of fractions, mixed fractions that come in. So that would be the next task for them to do. And then what I would suggest we would do, I'm just going to slide mine right out of the way, is you might even give them the opportunity then to go back to something like this. Can you model this again? So put it out with all of the different shapes and so they can see it in real life. And then we might ask, what fraction is the green in this picture of the whole? So now I really do need to know how many fit into each one of these pieces that I can see. And then I can express it as a fraction of a whole. So I'll leave that one with you just for a second because this one's worth doing and just seeing what you get. So just to revisit our shape, when we are talking about what fraction of the green triangles belongs to all of these, the students are going to have to remember that each hexagon has 6. Each of the red trapezoids has 3. Each of the rhombus has 2, and so on. And here's our large trapezoid, the pink one, which would have 5, but I also see that part of it is overlapping here. So we'd have those counts that need to happen before we would do anything. And then we would figure out what the total number is versus what is exposed. What do I see in actual fact? So that's really important. The other piece that you could do here is what ratios. You could say, what is the ratio of green triangles in this dinosaur picture to the hexagons or to the pink trapezoids? Or what is the ratio of the red trapezoids to the pink trapezoids, and so on. So it's not just, again, about just counting. It's also about how do I embed this in a new concept that students may be doing. So again, ratios would be one of those pieces. Okay, so now let's go one step further. And maybe we want to ask a student, I'm just going to put one of these down here so we can see it. So when we say to them, you know, what is the area? We know that we're covering our shape completely. So then we may ask them as, what is the difference between the area and the perimeter? And so again, we're going to use our unit of the triangle as our measuring tool. Notice we don't have a ruler here. And so we're going to do our area. We talked about area in terms of 1 unit squared, which was a triangle. If I change the unit that I'm going to use as my measure, my non-standard unit, then it'll change what my total areas are going to be for each of the shapes. Let's just stay with our consistent 1 triangle. So if I say that this was the area was covering it, then how is that going to be different than perimeter? So again, it's just getting students to think about the differences between total area covered or total surface coverage versus total distance around the outside. And so if we say to them that our 1 unit squared is 1 unit by 1 unit by 1 unit, this is my equilateral triangle, then I'm going to use that to figure out what is the total distance around my hexagon. So I'll actually line these ones up because I can see that each of the sides fit perfectly to my hexagon. And because each one of the sides on the triangle was 1 unit, regardless of which side touches, I have 1, 2, 3, 4, 5, 6. So the perimeter around a hexagon is 6. So then we could ask them, what is the perimeter around the red trapezoid? So again, I could do the same thing. I'm going to use my standard unit of my 1 triangle, 1 unit. So there's 1, 2, 3. And now they need to recognize that this will be 2 units long across the bottom. So what is the total perimeter of my red trapezoid? 1, 2, 3, 4, 5. And eventually they won't be lining them up because they're going to see that and they're going to remember. So we would encourage them then to decide what is the perimeter of the trapezoid? What is the perimeter of the boat? Right? What is the perimeter of the large triangle? And so on, using our standard measure of the 1 small triangle. So have them express what the total perimeters would be. And once they're confident in finding that, you'll also find that they're not necessarily going to measure each one of them because they're going to know. Then we might want to say to them, well, what if? So you knew that this one was 1, 2, 3, 4, 5, and you know that this one is 6. So is this one going to be 11? Is the perimeter of my new shape 11? And a lot of students will say yes initially because they think this is 6, this is 5. But now if we remind them that perimeter is the distance around the outside, and again, some of them might double check, yep, those fit. So this will be 1, 2, 3, 4, 5, 6. There's 2 here, 7, 8, 9. Oh. So that didn't quite work out the same. And the question would be, how is that possible? Well, in this case, I have 1, 2, 3, 4, and I have 5 sides exposed here. So the 4 plus the 5 exposed is 9 total because these two are already connected. I'm not going to go around each one of those 2. So then we can give them all different kinds of shapes. We could even go right back to our famous little dinosaur that we have here and say, wow, what's the perimeter of this guy going to be? And again, they would have the opportunity to double check it if they wanted to. But to find those differences between area and perimeter, again, they could take any shape that they've designed on their own and give it to a partner and say, what's the perimeter? What's the area? So just having some fun with the different designs that they've created. You could use any of those pre-made designs that we talked about before. So for example, I could take this one here and say, for our caterpillar, what is the perimeter of our caterpillar? This is one where they can actually put them on if they want to, and they can double check the distance here and the distance here and the distance here. So remember that his feet are also included. So then it just gives them another way that they can go through and add them up. Good counting and good summations, additions that we want them to work on. All right, so let's move into a conversation about a shape we haven't used a lot of. I don't know if these clear ones are going to focus too well, but here's just some different quadrilaterals that we have. And what we want to do is practice with our students to start talking a little bit about maybe angles. And so a corner angle, and I want to do all my angle measurements here without a protractor. So a corner angle like this, it's a corner in a room, we know is a 90-degree angle. So here's a 90, here's a 90, here's a 90, here's a 90. Or I have this large square down here, or I have this rectangle. What they have in common is that they all have 4 90-degree angles. In the square case, each of the sides are the same length. This one is the same thing. This one has 2 opposite sides that are the same length, but they're not all the same, all 4 sides. That's the definition of a rectangle. We could even have a conversation about, what about a trapezoid? It has 4 sides. But why is it different? How does it look different? Well, first of all, it doesn't even have the square corners on it, but it does have 4 sides. It does have some parallel sides, so we're getting into that conversation, but these sides are not parallel. So it's just having the quick, what do I know about quadrilaterals? What are my defining attributes that I can decide on and see? And what are the differences, similarities that I'm going to see? Where I want to go is if I'm going to measure angles of my shapes, what I want to know is if I were to take a square and break it in half, in other words, just chopped it right here with my saw, what would I end up with? Well, I would end up with 2 triangles, which is correct. Now, are they the 2 triangles that fit on here? The answer is no, they aren't. Right? So that's why we're not using that as our symbol. We're using just the conversation about what happens when I take a square and I cut it in half. And the students should be able to see, and they could even draw on here with a erasable marker, that I end up with 2 triangles. Now, it happens to be a right angle triangle. I'm not concerned about that so much. But what I want to go to is, how many degrees did we have in our square to start with? I had 90 and 90 and 90 and 90. So 90 plus 90 plus 90 plus 90 is 360 degrees. Is that true of the big square? 90 plus 90 plus 90 plus 90. Yes, it is. Would it be true of the rectangle? Yes, it would. 90 plus 90 plus 90 plus 90. So a quadrilateral that has 4 90-degree angles has a total of 360 degrees. And whether it's this little square that I cut in half, or this big square that I cut in half, or it's this one that I cut in the diagonal, I'm going to end up with 2 triangles every time. When I cut it diagonally, I end up with a triangle on both sides of my cut. So it's going to be exactly half of my shape that I had here. And if that's true, then if 360 degrees is my total, then half of that would be 180. And that means that every triangle, regardless of its size and shape, because obviously this shape doesn't look the same as this shape, has 180 degrees in it, because it's exactly half of a quadrilateral that had 4 90-degree angles. So if that's true, that every triangle has 180 degrees, then we could say, what made this little triangle so special to us? Well, we can say all the sides were the same length. And that's correct. It is. It's what we call an equilateral triangle. And the number of sides that are the same also tell you how many angles are the same. So in this case, I had 3 sides the same. So 3 of my angles will have to be exactly the same measure. Well, if that's true, 180 divided by 3 is 60, 60, and 60. If only 2 sides were the same, then I would have 2 angles that are the same measure. But we're working on this guy. This was our base. This was our starting unit for area, unit for measurement. So we're going to use that same one for length. We want to talk in terms of angles now. So this is 60, this is 60, and this is 60. So if I wanted to know how many degrees in each of the angles in a hexagon, wow, then I need to know something about this little triangle. Well, I know that I can put the triangle right there. And I know that that angle right there is 60 degrees. So if I put another small triangle on top of it and fit it right over top of my corner of my hexagon, then 60 plus 60 makes one of these big angles 120. So that means that my hexagon is 120, 120, 120, 120, 120, and 120. So I can add that up 6 times and get the total number of degrees in here is 720. But that wasn't our question. Our question was, what's the measurement of each of these angles? So I know that a hexagon has a 120. So what else do I know? How can I use that and the fact that I know my triangle is 60 to figure out the answers for what are the angles in here? What do I see here? Well, I see that it actually fits right over top of my hexagon. So this angle is also 120, and this angle is also 120. And we said that to make a rhombus, you put 2 little triangles on top, one on this way and one facing this way. We already know that this is 60 degrees, so then this will be 60 degrees. So I now know that a rhombus is 120 plus, this rhombus is 120 plus 120 plus 60 plus 60, which just happens to be 360 degrees. Remember, we said a 4-sided figure was 360 degrees. This one does not have right angles, but it does have the 4 sides on it. So again, I'm using my knowledge of this being 120 and this one each having 60, 60, and 60. So now we can ask the students a lot of things. We can ask them, well, what are the angles in this red trapezoid? How are you going to figure that out? Well, again, does this fit on top of my hexagon? It sure does. So these angles at the top here fit perfectly onto my hexagon. So this is 120 and this is 120. What do I know about the green triangle? Well, it fits right over the edge. So that means that the angles on the corners are 60 and 60. So again, it's a 4-sided figure. 120 plus 120 plus 60 plus 60 is again 360 degrees. Another 4-sided figure. So you get the idea of what students can do now. So now I can do the same thing here. What are the angles that I see here? Well, they could try a lot of things out. They could see if this fits over top of it, and it does, I can go this way. So I know this is 120 because it fits right in that corner. I know that this is 120. It fits right in that corner. I see that this one fits right on top. So each of those is 60. So this trapezoid that was red and this one that is pink actually have the same measurements, only they have a different length at the bottom, but it didn't change the measures of the angles. All right, what else can I find then? Well, let's try the purple one. How am I going to measure that? Let's try the large green one. How am I going to measure that? Let's try our chevron. What's the angles that fit in that? And remember, it always comes back to just some pretty basic shapes here. So as the students realize that really this hexagon and this little triangle can answer a whole lot of questions, then I can give them a question like this, where I can say, here's your boat. What are the angles that you see here? Well, I can lay a few things onto it, right? I can go through there. So there's lots of ways for them to come up with the answers here. This is not the only one, but what we want them to do is do it without a protractor. They can verify their answers with a protractor once they've learned how to do that, but it's not imperative for them to come up with that. So we want them to be able to measure angles of all the different shapes. And then, of course, we would want to challenge them. So if I were to start putting pieces together, you know, could I figure out what those angles would be when I slide them in? So do I know what it is? And we could also ask them, how far is it all the way around a circle? If the whole thing is covered, what would that mean? So we would get to 360, that conversation. So they should be able to take their basic understanding of those two shapes and apply it to virtually every other shape that we can give them. In combination thereof is how many degrees would I find in each one of those angles in that particular shape. Okay, so let's leave angles. And I'm just going to grab a whiteboard here. I'll try and keep it off of there for a bit. So just turn my light off and see if that helps with the glare. There we go. Okay, so what we want to do now is we want to also look at what are the other things that I can do with these pattern blocks other than putting them on top of one another. I could use this for basic math facts as well. What do I know about the number of sides of a hexagon? It has 6. So each one of these has 6. So double 6s is 12, or 2 times 6. So then it becomes a visual for their math facts. So now I see 6 plus 6 plus 6, repeated addition, which is the same as 3 times 6, which is the same as 18, and so on. And I could do that with any one of my shapes, right? It doesn't have to be always the hexagon. I could do that with my triangle. So again, I'm looking at my math facts for 3. So here I have 3 plus 3 plus 3, or 3 groups of 3 sides, which means I have a total of 9. So again, showing them the different ways that we can use this to demonstrate. So when I say to a student, how do you know that 4 times 6 is 24? How can you show me that? Well, they could create an array. They could give you a dot pattern. They could count out money. They could take any one of these shapes and show you the same thing. And if I don't have a 6-sided figure that looks the same, what would be my alternative to when I say 6 times 4, I could take 6 squares, right? And I could do it this way. So again, students should be able to see pattern blocks, not just for pictures. They should be able to see them as a way of me demonstrating algebra. And further to the algebra conversation, you could even say, you know, when I introduce the notion of a variable for the very first time to students, we're always saying, you know, you could use a cup, something has to be filled in the cup. I could also say 7 plus some unknown number is equal to 11. And what would my unknown number need to be? What would I need to add to 7 in order to get to 11? Whether they use a number line now to count, whether they count on from 7, however they're going to do it. So this can become my placeholder. I don't necessarily have to have it as a tile per se. Okay, let's try something else. What if we set up ratios? Just put my pen down here. Let's move these out of the way. So what if I said, I'm going to build a rocket? Okay, so there's my rocket. And if I wanted to build 2 rockets, I could set up an opportunity to say that one rocket is equal to how many blocks. So my very first rocket had 4 blocks in it. So rocket number 1 has 4. So first rocket is 4 blocks. The second set of rockets, or 2 rockets, is 4 8 blocks. So I'm setting up a proportion or a ratio, in this case, of what is the number of rockets to the number of blocks that I have. So my rockets versus my blocks. So if that's the case, then I might ask them, what do you think would happen on the 5th set of rockets? How many blocks would there be? So again, we can look at patterning, we can set up the ratios, we can show them how we would set up equivalent ratios, and to figure out when I have my 5th set of rockets or 5 rockets, how many am I going to have? So since I'm going for every one, there's 4, the answer here will be 20. And then I can ask them a variety, and they can model it, they can show it, they can double check it that way. So again, I can set up a ratio type of proportion. And again, then I would also ask students, can you create your own design that's in proportion, and write down what that ratio is going to be, and then have a partner figure out what the missing one is that you'd like them to look at. All right, I took a minute just to clear off my board, and I just want to finish up with a question that looks like this. I have a pattern, and again, I could ask students to reproduce it, but I could also include the notion of symmetry. So what if I said, this was my line of symmetry, or it was my reflection line? Then what we'd be asking students to understand and be able to demonstrate to us is that in a mirror scenario, if that line is my mirror, then I'm going to be building the same thing, just going in the opposite direction. So again, we could ask students to consider, what does it look like to be symmetrical? And what does symmetrical mean? And can they demonstrate that understanding to us? Can they explain that understanding to us? So if I put this in here, I'll put this in here. And they probably know a few things about angles now because we've been dealing with angles. We could even ask them what angles are in here. But we can have that conversation then about symmetrical shapes as well. So what I'm seeing on the left side, I'm seeing on the right side. They should be mirror images of each other. And how can I verify that? All those different, how can I show that they're the same distance? I could measure that piece. I can even see that the same blocks have been used. Nothing has been changed. So I hope that gives you some ideas of ways that you can use pattern blocks. This is by far just a very quick overview of the different things that we can do. There are lots and lots of things that you can do with them. Again, patterns, you can Google those on the internet. There's lots of books that come along with the resources. When you go to some of the manufacturers, they have binders with ideas in them, samples of things like this that you could do with students. Or better yet, we can say, can you create me a shape that's symmetrical, right? So then they have to remember what that looks like, and or what that means, and that they would create a shape that, and again, they could get really elaborate, and students love that kind of opportunity to build. So there's lots of ways that we can do this. It's not just about building blocks for fractions, and it's not just about attaching blocks to make a pretty picture. The picture should have a purpose. So whatever we give them to work on, it should be with intent in mind, not just for fun. They don't know the difference between fun. They don't know that symmetrical is really such a big mathematical concept. All they know is that they get to make a mirror image of it, and they're going to be building as they go. So it's very interactive, but also there is a very targeted learning opportunity in each one of those. So thanks very much, everyone. I hope that gives you some ideas of where you can go.